Hi everyone, welcome back to Topic 3, Accelerated Data Science with GPU. In the previous session, we gave an overview and introduction on QDF, which is a library of wrappers that can utilize GPU accelerated data frame to handle large data. In this session, we will be focusing on Qml, which is a library that implements machine learning algorithms and run machine learning tasks on GPUs. Qml is a suite of libraries that implement machine learning algorithms and mathematical primitive functions that share compatible APIs with other rapid projects. Qml enables data scientists, researchers, and software engineers to run traditional tabular machine learning tasks on GPUs without going into the details of CUDA programming. In most cases, Qml's Python API matches the API from scikit-learn. For large datasets, these GPU-based implementations can complete 10 to 50 times faster than their CPU equivalents. These can be referred to the Qml benchmarks. Qml also features multi-GPUs and multi-node multi-GPU operations using Dask for a growing list of algorithms. Qml API follows the scikit-learn API as close as possible, so people don't have to learn something new, and they still get the same ease of use as they get in scikit-learn. But it's built on the C++ APIs, which we can then accelerate with CUDA. And then on our side, we are like building these algorithms one by one and writing them exclusively for each other. Why don't we just break down this algorithm into classes of algorithm classes of problems, which then you can turn into primitives. And so we have solvers. We have dissonance matrix calculations. We have all these different machine learning primitives, as we are calling them. But we can layer them together, and we can build an algorithm, and we wrap that algorithm with Python that follows scikit-learn API. So the end users get a really fast algorithm. And under the hood is all this GPU acceleration. And even how we develop is fast because we take a very modular approach. Let's talk a little bit more about primitives. You know, there's a combination of linear algebra, sparse, random, statistics, distance, matrix, solvers, decomposition, and NVIDIA is continuing to build more primitives as they add more machine learning libraries. Because it is important to build more primitives to make it easier for this algorithm to be created and used. There's a list of different algorithms that we are trying to accelerate today. We have classification models such as decision trees, logistic regression, k-nearest neighbors. And we have regression models such as linear regression, support vector regression, gradient boosting. And we are working on some of the Bayesian inference, such as hidden Markov models. Then we have clustering algorithms such as k-means clustering, dbScan, dimensionality reduction techniques using principal component analysis, singular value decomposition. We are also working on some time series forecasting models as well, such as ARIMA and hot winters. So look at the structure here. And this is how we divide the world up into high levels and low levels. At the high level side, that's the Python side, where we use Dash to do distributed machine learning, both data and model parallel. And we have model parallelism and our CUDA C++ layer. And then we have all the primitives and GPU communication at the bottoms, things like MPI, etc. Let's take a look at an examples of clusterings. It's a pretty straightforward and simple scikit-learn interface. And firstly, we just load the moon's datasets by creating random samples and put them in a pandas data frame. Then we just convert the pandas data frame to QDF. Remember, QDF is the GPU accelerated data frame. And we just use the algorithm dbscan, which is also GPU accelerated. And we can call the functions like fit and predict. And we are off to the races. Besides the conventional algorithms, let's take a look at Umap. It is a new algorithm that can be used as an effective pre-processing step to boost the performance of density-based clusterings. It shows how they get about a 15 times improvement using Umap for some type of clustering applications compared to its CPU equivalent. Initially, we have another algorithm called TSNE. However, some limitations for TSNE is that TSNE doesn't scale well for rapidly increasing sample sizes, and attempts to speed it up lead to a large memory consumption, making it impossible to do the analysis outside of computer cluster. Moreover, TSNE doesn't preserve global data structure, meaning that only within cluster distances are meaningful, while between cluster, similarities are not guaranteed. Therefore, it is widely acknowledged that clustering on TSNE is not a very good idea. And Umap is much faster than TSNE when it concerns large number of data points or the numbers of data dimensions are greater than 3. Let's take a look at Qml regression examples. Try to recall linear regression. It is to perform the task of predicting a dependent variable y based on a given independent variables x, and drawing this relationship in a two-dimensional space produces a straight line, often referred to as a line of best fit. We can use linear regression for a lot of tasks, such as housing price prediction. We can also implement linear regression in Qml, which is rapid AI equivalent of scikit-learn, so that we can execute the analytics pipeline entirely on GPU. In part to show the similarities between scikit-learn and Qml, the demonstration makes use of the Boston house price dataset, which is found by default in scikit-learn. The dataset was taken from the StatLab libraries which is maintained at Carnegie Mellon universities. We will use QDF to load and build a GPU-accelerated data frame. In total, there are 506 instances, and each has 14 attributes. Knowing the layout of the Boston data and having an adjustable frame, it is time to work on defining and splitting training and testing data. We are ready to implement the linear regression model now. We set the column house price as the dependent variable y, and other attributes as independent variables x. For scikit-learn, we will import the linear regression function, feed the model on our training data, make predictions, and then calculate mean square error. The same functions are already integrated in the Qml libraries. Sometimes it is difficult to tell the model performance from the error score. Therefore, we will visualize the model using matplotlib. The multiple regression model produced pretty accurate predictions and was just as easy to implement. In this simple demonstration, we implemented multiple linear regression on the Boston housing dataset with the help of the Qml machine learning libraries. We can see that this high-level API of Qml is very similar to the ones in scikit-learn. And therefore, it is very easy for us to implement and scale up our machine learning models when we are dealing with huge data sets.